are keeping well. So let us continue our discussion on the partial derivatives. So today we are going to define something more general, which is called the directional derivative. As the name suggests, this is a notion of derivatives for functions of 2 and 3 variables in a specified direction. Okay, and then we also discuss the notion of differentiability. Okay, so differentiability is the most general situation where we do not have any preferred direction, we rather we consider all the possible directions simultaneously. All right, so let us just recall briefly. Okay. So look at this picture. This is the picture we had when we had the definitions of partial derivatives, isn't it? So what we did in order to compute the partial derivative, for example fx, you treat the function f as a function of x only, isn't it? And that means that we are keeping the other variable y constant. Okay, so if that is happening, then we are going to get these curves, because this is a curve when I have taken x equal to a fixed, and similarly this curve, if you look at it, this was the curve when we had taken y equal to p. So the intersection of this plane with the given surface is going to give rise to a curve on the surface, and then it becomes as the situation as if you are working with functions of one variables, isn't it? And then you had that at this given point there are two tangents, the t1 and then the t2 respectively, when we are fixing y and x, isn't it? And this picture on this side is basically a similar situation for a different surface. Okay, here this is drawn because one can see that the tangents more clearly, and not only that, this plane, if you look at it, this is a plane which contains both these tangents at the point P. Okay, so this plane has significance, and it is called the tangent plane. And what it is actually doing at this point, if you look at carefully, this is the surface, correct? This is the surface which can have bends and so on. And at this point we have got this plane which is tangentially at this point P, and what is actually doing is it's kind of approximating or giving you an approximation of the surface under consideration in a small neighborhood of this point. Okay, so this is how the derivative is perceived, if you recall, even in the case of a single variable function, correct? The tangent line, what does it do? It gives you how the curve is changing, and it gives you a linear approximation to that, isn't it? So basically we are going to just do the same thing over here also. So we start with a function, and let us say that these guys fx and fy, they exist, and then we have these two tangent lines at the point P as in the previous situation. Then the plane which contains these two tangent lines is called the tangent plane to the surface at the point P. Okay, so this is the definition. You can think of it as a definition, and you can easily write down its equation. Okay, this is the equation of the tangent plane to the surface x at the given point P. Okay, so you see that this is the slope of the tangent t2, and this is the slope of the tangent t1. So when you write down the equation of the plane, what you all just need, I think what you just need to do is just go back and write down the equation of the plane, and try to see that the constants here are going to be given by these partial derivatives. Okay, all right. And often this z is written as f of x comma y, and the c was f of a comma b. So if you write it in this fashion, you get this expression. Okay, so just look at it, stare it at this equation. What is it telling you? That no matter which f I started with, okay, because this x minus a and y minus b, these are meant to be very small, correct? X and y both are approaching a and b. So in a small neighborhood of the point a b, f of xy looks like this, and this is, you see, equation which has constant and the linear terms in x and y, correct? There are two more constants. So the advantage here is that you are able to approximate this f near the point a comma b in terms by a linear equation. Okay, so this is called the linear approximation of f. Okay, this you have to keep in mind that this is not a global situation. We are talking about at the point a comma b. Okay, and in a small neighborhood of that. Okay, and once you have this equation of the plane, you can also write down what is the normal. So yeah, and in some books you will find that this is they talk about the unit normal. So basically you have to normalize. Okay, so given a surface, this is the equation of the tangent plane. Okay, this is obtained by finding the t1 and t2, and then just going to the definition of plane, we can write down the normal vector to the plane. Okay, at a given point. So if you change the point P, the things are going to change. The tangent plane is going to change, and similarly the normal vector will also change. Correct? All right. So as I said in the beginning, that we try to generalize the notion of partial derivatives. Okay, so just write down the definition of partial derivatives once again. So this was the definition, correct? Of course we say that this limit exists, then the partial derivative. Okay, here change is happening in the y coordinate and x is kept fixed. So basically we are talking about fy, isn't it? Okay, now if I rewrite this, just rewriting it in this fashion, the x comma y plus h can be written like this, isn't it? So x and y, this is the point, so you put it together and the h, y plus h basically gives, can be obtained by this. You take the scalar h and then the vector 0 comma 1. Okay, and then this is as it is. So you notice here what is happening here, that you are basically looking the change in the direction of 0 comma 1. Correct? This h is the change and the direction is fixed by the vector 0 comma 1. Okay, so basically this is what we are doing. Now as you can guess that this 0 comma 1 is not really any important thing, or it's not doing anything. Okay, instead I could I could have taken any fixed unit vector. Okay, so this is what we are going to do, and it is going to give rise to the notion of directional derivatives in general. Okay, so as I have written over here, that fy is nothing but the derivative, or we are calling it partial derivative of f in the direction of the unit vector 0 comma 1. Okay, here unit, because if I take any other vector in the same direction, I can absorb the constant with h and consider the unit vector rather. Okay, so that is why you always write the unit vector when you are trying to compute the directional derivative. All right. So this is the definition. So you start with a function from R2 to R and take a specified direction. Let us call it u, when y this a comma b vector. Okay, and assume that this is a unit vector, that is the modulus is 1. Okay, then the directional derivative of f, as you can guess, is going to be defined by this limit. Correct? This is precisely the same thing. 0 comma 1 is replaced by a comma b. Okay, so the notation is different. The f suffix x and f suffix y, they are reserved for the partial derivatives, because they are the special ones. They are along the coordinate axis. Okay, whereas if you want to go in any given direction, then we are going to use this notation d suffix u. Okay, and if this limit exists, we say that the directional derivative of f at this point exists. Okay, and you can rewrite this again, because this is just the addition of two vectors, so you can also write it in this fashion. Okay, so what you need to worry about, you need to worry about whether this limit exists or not, and what is it doing. Like in the case of fx and fy, this is telling you that how the function is changing in the direction of a comma b from a given point. Okay, yeah, so as I always tell you, that always write down the definition, the corresponding definitions and corresponding ideas for the remaining part, which is here the functions of 3 variables. Okay, I have just defined this thing for functions of 2 variables. You can just complete it, and as I have been telling you, like the partial derivatives are just particular and special examples, and they have got special notations as well. Okay, so think of all those examples which we have already worked out, and try to see how does the directional derivative behave for those examples in some some specified directions other than the directions of the coordinate axis. Okay, so you take some vector like the diagonal or the anti-diagonal, or any line which you like, and then try to compute. Okay, so we will give you lots of examples where you compute the directional derivatives in some specified directions. All right. Okay, so now we define what is the differentiability in general. Okay, this so far we have just talked about the derivative in a given direction. Okay, now we are going to talk about, because we have functions of 2 and 3 variables, and if I allow both the variables to change simultaneously, in all possible ways, then what is it we are going to sorry, get. So just a second. So let us first recall that how do we define the derivative for a single variable function. Okay, so there what we have to worry about this ratio. So fx minus fa, where a is the point of interest, and you approach this a. So basically you have got fx minus fa. This is the values of f near the point a, and this is these are the points which are close enough to points, the given point a. And then you look at this ratio, and if this limit exists, you say that this is the derivative, correct? And it's basically going to give you a number if this limit exists. Okay, so I mean, if you just try to recall this, we have done also. What does it do? It basically gives you that how is the change happening in the curve, or how is the curve changing, and it does the other thing also which we talked about in the beginning, that it tells you that the fx can be approximated by a linear function, okay, in a small neighborhood of a. Okay, so this approximation is what we are going to pick up. The problem is this definition, if I want to consider functions of 2 or 3 variables, this does not really extend to that case, correct? Because I can't put here x minus, instead of x minus a, I can't put here x comma y minus a comma b, because that's a vector and I can't just take that over here. Okay, so what we have to do is we have to look at the interpretation of this in the following sense. So we just rewrite this equation in this fashion. Okay, you bring this f of f prime a on this side, and then x minus a is in the denominator, so you multiply it over here. I can write it like this. Okay, now what is this? This is basically telling me that fx is almost like this. Okay, not only that, even if I have divided by x minus a, this is going to go to 0. So what is it telling me? That fx is being approximated by this quantity on this, okay, in this underlined quantity, in such a way that even if I divide by x minus a, I still get 0. Okay, so that means this difference of fx and this quantity is going to 0 faster than this guy x minus a goes to 0. Okay, so this is called a good approximation. Okay, sometimes we use this term good approximation, that this is not only going to 0, but it is going to 0 faster than this thing. Okay, okay, so and what is this quantity? This quantity is nothing but the tangent line. I mean, you can just recall the definition, correct? Tangent line at a point a and fa, this is the point on the graph, and this is the slope. So this tangent line, basically what is it doing? This is giving you an approximation, not only an approximation, it's a good approximation, okay, of fx. So this idea, because we have talked about the tangent plane, is going to extend to the situation when we have functions of 2 variables and 3 variables, and okay, this is what we get. So you start with a function of 2 variables, okay, taking value in the r, and we say that this function is differentiable at the point a comma b if its partial derivatives fx and fy they exist, okay, at this point, and this limit exists and is equal to 0. Okay, so what is this limit? Again, look at this quantity. This is precisely the term which we had for the tangent plane, and this is giving you a good approximation of f at x comma y, which are the points near a comma b. Okay, and in the denominator what you have the difference, the distance between the point x comma y and a comma b, and I am not putting any special direction here. I am saying whenever this x comma y goes to a comma b, this is in the sense of limit of two variables. Okay, so that means you have to take small neighborhoods around this point. There is no specified direction here. Okay, so if this happens, you say that your function is differentiable. Okay, and if we just rewrite this, so these two quantities here, I can rewrite them in terms of the dot product. Okay, so I collect the derivative terms, the partial derivatives, and then the constant terms. So this gives you a point near a comma b, and this is the derivative, the evaluated at the point a comma b. So we have that the function is differentiable if you have got the partial derivatives at that point, and this limit is 0. Okay, and this quantity here, this is a vector, is referred to as the derivative of f, and in this case we are going to use the usual notation f prime. Okay, so this is here, vector is no longer a number. Okay, now it's a vector. So the derivative here of two variables is no longer a constant, rather it is a vector given by the partial derivatives evaluated at the point a comma b. Okay, so if you try to compare this definition in some of the books, a priori it might look a little weaker, because I have assumed that the partial derivatives exist here. Generally the definition is given that if there is a vector, okay, which I have written here fx and y, so if there is a vector alpha such that this limit exists, then you say that the function is differentiable. Okay, but that will tell you that vector alpha has to be the vector which is this one. Okay, that is the partial derivatives. So but this is slightly more easy to grasp, because we have just seen that how the tangent plane looks like and so on. So this is the reason I have written it in like this. Okay, so you don't have to worry about it. So this was the situation when I am dealing with a function of two variables. Okay, now I can also do the same thing when I am dealing with functions of three variables. So just for the sake of clarity, we just write it down. Okay, here I could not write limit because this space doesn't allow me, so I am saying that this goes to 0 as x comma y comma z goes to the given point. Okay, so I have put some notations, but you should write it on a piece of paper. So this term is precisely the analog of this term over here. Okay, so you just do that. Okay, and you can also say that this x, y and z, you can replace them by a plus h, by plus k, and b plus k and c plus l. Okay, and then allow h comma k comma l go to 0 0 0 0. Okay, so this is just the matter of notation. Okay, but please write down each and everything for both the cases, the for the functions of two variables as well as for three variables. Okay, so once I have this, there are some observations, some small results. Yeah, so the first one is this is very much in line with this case of single variable functions, that if I have a differentiable function, that function is always continuous, isn't it? And you will notice here that all the previous notions of derivatives, like the partial derivatives and directional derivatives, did not allow us to conclude this result. However, if I have the differentiability, because this takes care of all possible directions, then I do get that function is continuous. Okay, so let us see that. So you start with a function. Here I have started with function from R3. So this is just I keep changing R2 and R3, so that you are not losing track of that, that we are working with both. All right. Yeah. So what you do is you take a function from R3 to R and assume that's differentiable at a given point P, then the function is continuous. Okay, so okay, let me just see that how. Okay, so some notations, because so that things fit on the page. We will write this x minus a, because this is what we are going to take it to 0. So I write this as h comma k comma l and denoted as the vector h. Okay, and I use the notation alpha for this vector, the partial derivatives evaluated at the point P. Okay, so what we need to see? We need to see in order to check that function is continuous at the point P, we need to see that this difference goes to 0, isn't it? Because h comma k comma l, this is going to the 0 vector. So if h comma k comma l, this goes to 0 vector, or the capital S vector here goes to 0, this difference should go to 0, correct? This is the meaning of continuity. Okay, so what we have the differentiability at our hand, so we are just going to make use of that. Okay, now differentiability, the definition of differentiability, if you remember, it has got this thing in the numerator. Okay, I just go back here. The f at the point close to a comma b comma c, and minus f of at a comma b comma c, and then this, the partial derivatives minus this, I mean the inner product or the dot product with h, and in the denominator is the distance. Okay, so the quantity in the numerator is basically this. Okay, with these new notations, alpha is the vector with partial derivatives evaluated at p, and h is this. Okay, and what we know that this quantity goes to 0 faster than the denominator, isn't it? What is denominator here? It is going to be just vector h, the modulus of that, isn't it? So basically what we can write is that this quantity is this much times something extra which goes to 0, because I know that the numerator has to go to 0 faster than this modulus of h, isn't it? So that it has to be minimum this, and there is going to be an extra quantity which goes to 0. Okay, so here epsilon h is just a function of h which goes to 0 as modulus of s goes to 0. Okay, so once I understand this, I just have to plug in the things, because I need to compute this, so I write it down, and the information is in terms of this extra quantity here. So in order to get this quantity, I subtract it and then add it, correct? And now I know that I have some information about these three quantities, so I separate them and apply the triangle inequality. Okay, now just substitute this first one over here, and the second term, modulus of alpha dot h, this is the dot product of two vectors. So this is Cauchy-Schwarz inequality will tell you that this is less than equal to the modulus of alpha times modulus of h. Okay, now you see that both these quantities go to 0 because this alpha is just a constant. Okay, the modulus of alpha is just a constant. So you get that this difference goes to 0 as mod s goes to 0. Okay, so this is very easy, and the proof is also exactly the same argument as you do for the functions of single variable. Okay, so now let us look at some examples. Okay, this is an example which we had seen earlier. Okay, so what we had this function, okay, when x and y non-zero, and at the point 0 0 it is just defined to be 0. Okay, if you remember, we proved that the partial derivatives at the point origin, because this is the point which can be of some problem, so we saw that the partial derivatives exist and they are just 0 0. Okay, but at the same time we also checked that this function is not continuous. Okay, we had checked this. Now if something is not continuous, it cannot be differentiable, because we just had a small result. Okay, so you don't need to check here differentiability, you don't have to go to the definition, because you just verified that this function is not even continuous. So you can straight away conclude that this function cannot be differentiable at the point origin. Okay, so this is an argument which is going to be useful in many situations. You just see that the function is not continuous. Okay, but one thing is, like the partial derivatives here exist, you see. So existence of partial derivatives doesn't allow us to conclude continuity. Okay, so this example is also giving you that even though the partial derivatives exist, but my function is not even continuous. Okay, you need differentiability to conclude that. Okay, but of course it can be used to show that something is not differentiable, that if it fails to be continuous. Okay, now let us look at another example. Okay, this example also I had given you to compute partial derivatives and the higher derivatives. Okay, so computing the partial derivative, if you do, you will see that fx and fy, they are just 0. Okay, so alpha is going to be the vector 0 comma 0, and then you take h, this is not 0 0. You have to take h is small h and small k, where h and k goes to 0. Okay, so correct this. Okay, this is not so h as in the previous one. Okay, h is this thing, and then what we need to consider this ratio. Okay, I have put modulus because if I want to show that some number goes to 0, and if I can just show that the modulus of that goes to 0, then I am done. Okay, so look at the modulus. Now f of hk is given by this, because h comma k is non-zero, and f00 is 0, and you see that alpha vector is 0, so the dot product is also 0. So this quantity both are 0. All you have this divided by modulus. So just put it over here. Now you see the h square minus k square divided by h square plus k square. This quantity is always less than equal to 1, isn't it? No matter what h and k I take, because this quantity is always less than equal to the quantity in the denominator. Okay, so I just take or replace this by 1. This is not good, with a less than equal to sign. Okay, and then I will be left with modulus of h, modulus of k in the numerator, and in the denominator modulus of this vector h. Okay, but h is always less than equal to modulus of capital H, isn't it? Because h is less than equal to square root of h square plus k square, which is modulus of the vector h. And then the same thing will happen for k. So if I put a less than equal to sign and then replace this h and k by modulus of h, I get a square, and the denominator I have only a single power of modulus h. So I see that this goes to 0 as the vector h goes to 0, or modulus of h goes to 0. Okay, so we conclude that f is differentiable at. Okay, and what is helping here? This power 2. So this power 2 is coming because I have used something on h and k both. Okay, so this also suggests that if I had only h here or only k here, things may not be the same, isn't it? Because then I won't have this extra power. So what you do is try to take some different powers of x and y and see that which powers, or is there a condition on the powers, so that I get a function which is differentiable at the point 0, 0. Okay, so this is how we have to approach, and some examples are going to be straightforward, but some examples you have to think, and so on. So today I will stop over here, and in the next lecture I will try to build on this, define some new notions which are related, and slowly move on. Okay, so all right.